Thank you. Thank you, Dr. Dilip Kumar. It is really great honor for me to chair this session in this symposium, which is conducted as a part of the International Conference on Special Function and its Applications 2021, organized by University of Kerala, India. For today's session, we have eminent speakers. The first one is Professor Virginia Kiryakova from Bulgarian Academy of Sciences. She actually doesn't need any introduction. She has done prolific work in this area of special functions, and especially she's editor of very highly reputed journal, Fractional Calculus Analysis and Applications. So all the researchers in this field know her mastery over this field. So it is real pleasure to welcome for this lecture. So over to Professor Virginia.
Thank you, Professor Varsha. Thank you for the invitation from you and all organizers to give a talk at this symposium inside the international conference. And okay, I can continue with my talk. So you see the title, and next slide, please. Yuri. Let me tell you that the results I briefly survey here are based on some of my earlier publications, starting from the book of 1994, Generalized Fractional Calculus and Applications. But later, this idea was emphasized and collected in some recently published survey papers, starting from 2017, say fractional calculus operators of special functions. The result is well predictable in the journal House Solitons and Fractals. Then the next title you see again from the same year. Then it was a commentary to another paper by other authors in 2019 in Frontier of Physics. And the last in these slides, you see the fractional calculus of some new but not new special functions, as with K indices, multi-indices, S analogs, and so on. So next slide. Continue with these more recent publications. Two of them are in the Handbook of Fractional Calculus with Applications, Volume 1, edited by Henry Machado, Wuchko, and others. And in these two papers, two chapters, me and also joined with Wuchko, we exposed briefly the theory of generalized fractional calculus, where the special functions are used in the kernel. And the last two papers are very recently published in Mathematics by MDPI. This unified approach to fractional calculus images of special functions is basically the work on which this talk is based. And next one is with more wide aiming, a guide to special functions in fractional calculus appeared this year. Next slide. Since the abstract in the abstract books was reduced to the first paragraphs, I here copied some of the text from the abstract. You see that the results exposed here are results from more than 30 years of my research on the area, and it provides some general results that hold for all operators of generalized fractional calculus that include the Riemann-Liouville, Erdős, Kober-Saigo, Marichev-Saigo, Maeda, and many other operators which are compositions of the classical fractional calculus operators, and the result holds also for all generalized hypergeometric functions as the right function psi q the PFQ function, the Fox-H function, the Marge functions. In this way, the result incorporate very wide classes of special and elementary functions, among which are the multi-index Metaclavia functions. Next slide. The aim is to save the efforts of many recent research made on this topic, where the authors evaluate images of some fractional calculus operators of some special functions, all in these particular cases following the standard procedure. Practically, the job is to calculate improper integrals of product of different special functions. And we can base also on a very general formula well known for integral of product of two H functions or two G functions of Meyer. Okay, next. Here is a very short intro. The audience is well know these functions, but just to have their denotation, the right, or also called Fox-right function, P-psi-Q function, you know very well. And it is also a case of the Fox-H function, and under some conditions written here, these are entire functions. This is also from works of Lutko, Trujillo, and in all basic books on special functions and fractional calculus. Next. And especially when the capital parameters A and B are all one or rational one, then the H function reduces to G function, and the P-psi-Q function 3 is reduced to the more popular PFQ function, you see. So in some cases, we can work in some simpler special functions, which are the classical special functions. Next. A few words about the Metaclavia type functions, one with 1 and 2 parameters. These are fractional indices analogs of the exponential, trigonometric, and other elementary functions, but they are solution not only of integer order equations, but of differential equations and models of fractional order, or even of fractional multi-order, if we consider the introduced multi-index Metaclavia functions in formula 5, you see. Instead, one gamma function in the denominator, we have several gamma functions with different parameters, with set of parameters, also called vector index Metaclavia functions. And we show that most of the special functions, especially in fractional calculus and in classical mathematical physics, are particular cases of these functions, or at least of the right generalized hypergeometric functions. Next. Just to convince you of how all these functions go as cases of the multi-index Metaclavia functions. Some examples. For m equal to 1, this we have the classical Metaclavia function. Also the exponential, cosine, sine, and so on. The error function, incomplete gamma function, Rabotnov function, the functions of Lorenzo, Hartley, and many others. For m equal to 2, in 1960, Armenian mathematician Jurabashan introduced Metaclavia type function with 2 by 2 indices. You see this number 6. And it was not very popular because the article where it's published was only in Russian language. But we have many examples of special cases of this function. The most important one is the classical right function 7, and also its particular cases as Menardi function Airy functions, and many other Metaclavia type functions on 3 or 4 indices. Next. For m greater or equal to 2 arbitrary m, we have the hyperbasal functions of the Lure as a special case, which appear as eigenfunctions of the hyperbasal differential operators, and as rare cases also the Laguerre exponentials. About Laguerre exponential, let us note that in several works by the Tolle, Ricci, Gara, Gorska, and so on, they considered the so-called Laguerre derivative, dl, you see, and it iterates m times, iterates dml as written here. And you can easily see that these are very special cases of the hyperbasal differential operators introduced by Rimouski 1966, the operator B, and even the iterates of Laguerre derivatives were considered by Ditkin and Prudnikov in 1963 in operational calculus. So based on this, we can see that the eigenfunctions of the iterated Laguerre derivatives, E1, E2, EM, and so on, that satisfy the eigenvalue problem here. The last line are nothing but right generalized hypergeometric functions with the index 1m plus 1 or even the simple one. So these are functions, not only generalized hypergeometric functions, but also cases of the hyperbasal functions of de Leroux. You see the functions defined by equation 9, or the simpler case, more visible, are the Bessel-Clifford functions of order m, the last equation. Next one. So, based on this, we see that the Laguerre exponentials are not only Bessel functions or Clifford-Bessel functions of order m, but also multi-index Metaclavia functions in a rather simple case. And also can be seen as examples of the multi-index Robotov function as below. So all this and the so-called Richel function, EMZ, is also interesting to note that it is a case of the original Leroy function, which was extended to fractional indices by Gerhardt, Gara, Polito, Menardi, and so on. Next. Okay, few slide words about more general Laguerre type generalized hypergeometric functions, the functions L, P, F, Q, but you see they can be represented as PFQ plus 1 functions, and also fall in our scheme. Same is for the generalized exponential integrals by Menardi, Messina, Paris, and others. That can be represented as the last equation on the slide. Next. So, few words about other new so-called new special functions. There are introduced the so-called K analogs of various special functions, and these are based on the K extension of the classical gamma function, and also on the K Pochhammer symbol used in their denotation. But it is easily seen that the K gamma function is nothing but a classical gamma function. And in all definitions, we can put the classical gamma function and see that these K functions are also classical special functions in the most cases, right generalized hypergeometric functions, and we can use the general results for them. So next. Next, please. All these about special functions were presented in my recent survey in mathematics, a guide to special functions in fractional calculus. The title inspired from the guide to mathematical functions as Bateman planned to have this Bateman had the now very famous book. Next one. A few words about the operators of generalized fractional calculus. We consider so-called multiple Erdős-Cover integrals. You see, instead of Erdős-Cover operators with gamma, delta, xorta, beta, we consider compositions of these operators, and the definition is first introduced by single integral with special function h function in the kernel in the formula 10, where delta 1 to delta m are the multi-order of integration. And we have also other multi-indices, gamma and beta. In the simple case, when all beta are equal between them, we can present also the operators of generalized fractional calculus by simple Marge function. Next. We have also definitions for the corresponding generalized fractional derivatives. You see, we have special explicit representation of the differential operator, which is formula 14, that is used instead of the classical differentiation, like in the definition of the Riemann-Liouville definition of fractional derivative. And with Luchko, we also introduced the Caputo type analog of this. Next one. Next, please. Yuri?
Yes, just moment. Something is going wrong.
Here. Next
Okay.
one.
Next.
Yeah. Okay. Just few examples. Next slide, please. With examples, for m equal to 1, we have the classical Erdős-Cover operators, the Erdős-Cover integral and the Erdős-Cover derivative, as seen in 16. And very particular cases are the Riemann-Liouville integrals and Riemann-Liouville derivatives. Next one. We see that our result is based on the decomposition or composition result, that the integrals that we defined by means of single integral with h or g function in the kernel can be also represented by multiple integrals as composition of classical Erdős-Cover operators. And this is the key to very wide applications of these operators, because they consist of compositions of commuting Erdős-Cover or Riemann-Liouville operators. Especially for m equal to 2, the kernel function, the Gauss function, h with indices 2, 0, 2, 2, appear in special cases. And here we have the SIGO operators as more popular in the fractional calculus, and also many other hypergeometric fractional integrals. But for m equal to 3, the Marichev and later SIGO and Maeda introduced some operators where the kernel function is the Abel F3 function, or call it also Horn function. And we can see that this function is exactly the kernel function of our general operator for m equal to 3. And for m greater than 2, arbitrary 1, when we have multi-order integration or differentiation 1, 1, 1 that is integer but multi-order, we have the hyperbessel operators of Dimos. Next one. So we go now to the main topic just for a few minutes of this survey. Well known as some very old classical results, but Erde, Askey, Lavoie, Osler, Tremblay, and so on. They have in their books and lectures say the Riemann-Liouville images of PF cofunction. Also, the Poisson integral 20 is nothing but the Riemann-Liouville operator of the cosine function, and so on. Next. And for the Erde-Kober operator with arbitrary indexes gamma, delta, and beta, where delta is the order of integration, we have now the simple but general results for the image of P psi q function. You see that always when we apply once Erde-Kober or Riemann-Liouville operator, the result is the same kind of function, but the indices P and Q are always increased by 1. And the same result we have similar for the fractional derivatives. Next one. So using the composition property of the generalized fractional calculus operator, we have the following idea. If we apply once Erde-Kober operator to P psi q function, we increase its indices by 1. A next application of another Erde-Kober operator again increase the indices by 1, and so the final result you see in Theorem 1 is the generalized fractional calculus integral of P psi q function with also additional powers and arguments is always a same kind of function where P and Q are increased by M, where M is the multiplicity of the operator. Next one. In the simple case, we have the corollary for the PF cofunction, and we have similar results for the generalized fractional derivatives with changed arguments, but again, this P plus M, Q plus M psi function. Next. So examples are in many earlier papers, say to have the Riemann-Liouville operator of Bessel function, and following our corollaries, it is immediately seen that the result should be from 0 psi 1 goes to 1 psi 2. Next. Also Riemann-Liouville operators of Bessel-Maitland functions. Then next slide. The same follows for the classical White function when the Riemann-Liouville operator is taken, and we have you see 33, the last equation, that right function with the indices mu and gamma goes to same kind of functions, but gamma is increased by the order of integration delta. Next one. For SIGO operators, as mentioned, these appear as special cases in our operators for m equal to 2, and then we consider them as compositions of two commuting Erde-Kober operators. Next one. We can have many examples from other papers, earlier papers, that SIGO operators of Bessel function gives the predicted result. Next one. Also in the general case, we take right generalized hypergeometric function. The SIGO operator maps it to same kind of functions with P and Q increased by 2, because these are compositions of two Erde-Kober operators, similar for the derivatives of the SIGO operators. Next. For the very popular recently march of SIGO-Maed operators, we have the case m equal to 3, you see the representation of these operators like as they defined 39, where the F3 upper function is in the kernel. But the last equation from Rudnikov and the handbook integral of special functions, we can find the formula that upper F3 function is our function, the kernel functions for m equal to 3. So next one. Then we have these operators that can be represented as compositions of 3 classical operators of fractional calculus, and we can apply our general results. Next one. So in the general case, we have the MSM operator of P psi q function. That is always same kind of function where P and Q are increased always by 3. And naturally, many examples from other papers have the results which are well predicted by our general results. So next one. Here are the examples of the so-called generalized Bessel functions, Bessel-Struve functions, and so on. All these are presented as right functions, P psi q, and then the result can be applied. Next one. The same come for generalized multi-index Metaclavia functions by Agarwal, Rogozin, Trujillo. And again, we have the predicted result as written is 43. Next one. Again, this is an example of fractional derivative in the sense of Marchev-Saigo-Maeda, and the result is also well predicted as this 2 psi 1. Next one. So we have the similar examples for the so-called generalized M series. You see here, this was introduced some years ago as combination between the PF cofunctions and Metaclavia functions, and we have the same results applied there. Next one. And with many examples, special cases. So next one, please. And a few words about if we apply the Erdős-Haber operator to multi-index Metaclavia function, the single case one operator, we have the first equation, and then as examples, we can show that the generalized fractional integral of multi-index Metaclavia function is the same kind of function where the parameters beta are increased by the multi-orders of integration as in 47. So next, it was a commentary about a very special case. You can skip there and go to next one, where we consider the authors as cited there, consider the Lumel-Wright function. And this is again special case of our general results. Next one. Also next. I told you about some new special functions as claimed with K-analogs, S-analogs, and so on. These are in this my paper. And next, please. For example, the K-Bessel function, you see how it is defined, but if we replace the definition of K-gamma function by the classical gamma function, we see that it is again just a classical Bessel function. And so we can apply our results. Next one. The same for the Marchev-Saigo-Maeda operators can follow easily. Next one. There were considered so-called even K-analogs of Metaclavia functions and of multi-index Metagrapher functions as defined at the two functions here, but all this are also reduced to write the generalized hypergeometric functions. So next one. Okay, and also there is so-called S function. You see the definition S with many indices here, which is reduced to the commodity Metaclavia function in special case. And next, you can see that this S functions is representable again as right generalized hypergeometric functions with parameters p plus 1, q plus 1. And all results we have follow for images, fractional calculus for this S function. Next one. And here more and more next so-called extensions, which are nothing but again the classical special functions and the right generalized hypergeometric functions as seen in 48. So nothing new. And next one. So conclusions, just instead of doing the work for all particular cases, we can make advice first to check if the special function you consider can be represented as a right generalized hypergeometric function, or in more general cases as Fox-H function and Margi function. We have formulas for them. Then check if the operator you would like to evaluate is some of the cases of the generalized fractional calculus operators, and then apply the results, the general results. We mentioned it shortly. And again, I remind that these are exposed in the survey paper in mathematics, volume 8, where the guest editor was Professor Luchko. So thank you for your help to present the slides. Thank you for attention. Yes.
Yeah. Thank you, Professor Kyriakova, for very interesting talk and such a deep relations and so many extensions. So it was really a wonderful talk. So
I'm
any
sorry
questions?
for some minutes we lost for adjusting the sharing, but okay.
Oh, may I ask a question, please?
Yeah, please.
Yeah. So thank you, Virginia, for your wonderful presentation. And indeed, we could see that your approach can cover a lot of different special cases. And my question is, are you aware of some reasonable cases where your approach cannot be applied? I mean, some other operators probably, or some other special functions.
Frankly said, the papers I have cited in all these surveys and reviewed or seen, all of them, in all of them we can apply this. But surely there are some operators where do not fall this composition of classical edge cover operators, or some special functions that are not the right generalized hypergeometric functions, say. So we can extend the results, of course.
And I think in particular for the so-called space fractional derivatives, like there is a fractional derivative or there is fractional derivative, so they are different. They are different.
Yeah. We can try to do this. Okay. Thank you, then.
Yeah. Thank you.
Okay. Thank you. So
thank you,
now
Professor Virginia, for your nice presentation. Professor Virginia, I have just one query. The number of papers in the direct application of fractional calculus. If suppose we think about the fractional operator, like Riemann Level or Caputo. Is there any paper can you suggest where this direct application of these fractional operators are coming?
Yes, many of these are cited in my survey because now you cannot combine. Yes, I can send you papers and so on. Okay.
Okay, thank you.
Okay, so we can we thank Professor Virginia for her wonderful talk and move on to the next speaker. The next speaker is Professor Iva Kaslik. She is from West University of Timisoara, Romania. She has her expertise is in the area of dynamical systems, neural networks, qualitative theory of impulsive and fractional order dynamical systems, and related areas. She has more than 50 papers to her credit. Very young and enthusiastic, active addition to the fractional group. So I am really happy to welcome her to this conference organized in India. And I hand over the mic dais to her. So please, Iva.
Thank you very
Professor
much,
Iva.
Professor Gedji. I hope you can hear me.
Yes,
can you
yes.
hear? Okay, thank you
Yeah,
very much
yeah.
for the kind introduction and also the invitation. It is really an honor for me to be present here, also to attend the talks of Professor Kyriakova and Professor Luchko and Professor Menardi, whom I admire greatly. I will try to share my screen and hopefully it will work. Okay, can you? I think you can see my slides. Okay, so I will start my presentation. My talk will be about the role of the Prabhakar kernel in the proof of Martinion's theorem, because my main interest basically in the is the stability theory of fractional order dynamical system or fractional order systems in general. So when Professor Gedji invited me to this symposium on fractional calculus and special functions, I thought about presenting this talk about the role of the Prabhakar kernel in the proof of Martinion's theorem, because it is something that we came upon this year, early this year, with my former student Juana Brandibur and Professor Roberto Garapa, when we were writing a review paper about the stability of multi-order systems of fractional differential equations. So let me just see if I can move my slides. Okay, just a second.
You make it full screen also.
Yes, okay, I made it, okay, and now it's fine, right? So
yeah, it's fine.
Now it's fine. Okay, so this will be the outline of my talk. I will present just some generalities about the Prabhakar function and its asymptotic properties, and then an introduction about the Prabhakar kernel and its properties, because this is what we will actually need in our proof. Then some generalities about the stability concepts in fractional order systems, and then I will present the original version of Martinion's stability theorem, as well as a slight modification that we came upon, as I told you earlier, this year. And finally, I will present some examples. So the Prabhakar function was actually introduced by Tilak Raj Prabhakar, an Indian mathematician who studied convolution integral operators, which had a generalization of the Metagrapher function as kernel. And this is the original paper of Prabhakar back in 1971, which was published in the Yokohama Mathematical Journal. And it has not received so much attention until the early 2000s, when actually the connections with the Havriliak-Nagami dielectric model have been discovered. Starting from the early 2000s, operators based on the Prabhakar function were employed to describe in the time domain relaxation models in several areas. And I have just mentioned here two references, but there are many dealing with applications of the operators based on Prabhakar functions. I just mentioned here the paper of Roberto Garapa, Professor Menardi, and Guido Maion, and also another paper of Andrea Giusti and Professor Colombaro. All right, so the Prabhakar function is actually a 3-parameter Metagrapher function. I have also seen Professor Kiryakova mention shortly the Prabhakar function as a special case in one of her slides. It is defined using this series representation. Some of the properties of this function, well, it is an entire function of order 1 over alpha and type sigma equals to 1. Obviously, when gamma is equal to 1, it reduces to the 2-parameter Metagrapher function. And also, an important feature of the Prabhakar function is that it provides a very simple way to express derivatives of 2-parameter Metagrapher functions. So namely, the mth order derivative of the 2-parameter Metagrapher function can be expressed as m factorial times the Prabhakar function with the coefficients alpha, alpha m plus beta, and m plus 1. Maybe a shortcoming is that an analytical representation of the Laplace transform of this function is not known, but we will actually work with Prabhakar kernels, for which the advantage is that the Laplace transform or the formula for the Laplace transform is known. Okay, now I will talk a little bit about the asymptotic properties of the Prabhakar function, because these are mainly the properties that we are using in our proof of Martinion's theorem. The asymptotic behavior of the Prabhakar function for large arguments in the complex plane has been studied in several papers, and I have mentioned here the early works of Paris, and also the paper of Roberto Gara and Roberto Garappa, and also the survey paper, which has been recently published in Fractional Calculus and Applied Analysis with the group of Professor Menardi, which includes all the properties of the Prabhakar function as well. So basically what we have is that the asymptotical behavior of the Prabhakar function can be described in this way as the absolute value of z goes to infinity, where we must emphasize the fact that in each of these formulas, the first term represents the dominant term. And what can we notice is that we have an exponential expansion given by this function f, which is dominant in this part of the complex plane, while we also have this algebraic expansion defined by the function a, which is dominant when the argument of z in absolute value will be larger than alpha pi over 2. Okay, there are these coefficients ck in the exponential expansion. It is important to notice that these coefficients are the coefficients in the inverse factorial expansion of this function f, as the absolute value of s goes to infinity. And details on how to compute these coefficients ck have been given in the previous works of Paris and of Roberto Gara and Roberto Garappa. Okay, so this is the asymptotic behavior. This is how we can express the asymptotic behavior of the Prabhakar function, and this will be very useful for us when we are talking about the asymptotic behavior of the Prabhakar kernel. I will move on to the next slide. Here we have a very nice graphical representation of the asymptotic behavior corresponding to several regions in the complex plane. So we can see here the Stokes line and the anti-Stokes line respectively, and also the fact that in this region, the exponential expansion is the dominant part, and in the rest of the complex plane, the algebraic expansion is the dominant part, which is very important, as we will see later on. Okay, so I will continue with some generalities about the Prabhakar kernel, which is defined in this way. So again, we have three parameters alpha, beta, gamma, and also an additional complex parameter lambda. And so the value of the Prabhakar kernel at t and lambda is t to beta minus 1 times the Prabhakar kernel function computed at t to alpha times lambda. Here t is positive and lambda is complex. As I have mentioned earlier, an advantage of the Prabhakar kernel is that we have an analytical a quite simple analytical representation of its Laplace transform, which is given by this formula here in the region of complex numbers S with positive real part and absolute value larger than the absolute value of lambda to the power 1 over alpha. And most importantly, we can obtain the asymptotic behavior of the Prabhakar kernel based on the asymptotic behavior of the Prabhakar function, and we can express it in a quite simple way as t goes to infinity. So we can see that again we have an exponential dominant term in the case when the argument of lambda in absolute value is smaller than alpha pi over 2, and we have an algebraic term, a leading algebraic term here, as if we are in the other part of the complex plane. Again, what has to be emphasized here is that the sign which appears in this exponential is considered to be positive if the parameter lambda is in the upper complex half plane and negative otherwise. I have also included another important property of the Prabhakar kernel, that is, it is completely monotonic if and only if these conditions hold. And actually, this is quite important as the Prabhakar kernel also appears in a lot of relaxation models and applied areas. Okay, now what I would like to talk about shortly is some concepts, some stability concepts for general n-dimensional fractional order systems with Caputo derivatives. So I have just considered this system where the fractional orders could be multiple, so not necessarily exact equal fractional orders belonging to the interval 0, 1. The function f is considered to be continuous on the whole domain of definition and Lipschitz continuous with respect to the second variable. We will assume that the null solution is an equilibrium solution for this system, and for some results on the existence and uniqueness of the solutions, I would like to refer to this paper of Dieter, Sigmund, and Tuan, who have considered this multi-order case very recently. Okay, so I have several definitions. Of course, the definitions of stability and asymptotic stability of the trivial solution are similar to the case of classical integer order dynamical systems. What is new is this concept of, or new, not new, but actually different in the fractional order case, is that we can introduce this concept of asymptotic stability of order t to the power minus alpha. Which actually means that the solutions will converge to the trivial solution as t to the power minus alpha when t goes to infinity. And this is also closely related to the Metagrapher type stability as well. So the important thing to notice here is that in fractional order systems, we will not have exponential decay, but we will have algebraic decay towards towards 0 in the case of asymptotic stability of the trivial solution. Okay. And next, I will focus on single order linear systems of fractional order differential equations, and this will bring me to Martinion's theorem. So now I simply have an autonomous linear system. The matrix A is a constant n-dimensional matrix. Obviously, when we analyze the stability of such a system, we can also build up the characteristic equation associated to this system, which is of this form, determinant of S to Q times I minus A equals to 0. And there's a very simple proposition that can be obtained, that is the linear system, our linear system is asymptotically stable if and only if the spectrum of the matrix A is included in the set SQ, where SQ is the so-called stability region defined by the set of all complex numbers lambda, such that S to the power Q is not equal to lambda for any S with positive real part. And actually, starting from this proposition, we can also arrive to Martinion's theorem, which gives us a simple condition which has to be satisfied by the argument, by the eigenvalues of the matrix A, so that our system will be asymptotically stable. So actually the result of Martinion has been presented in 1996 in this paper, so almost or let's say more than 25 years ago. And it states, the first statement is that the linear system will be asymptotically stable of order t to the power minus q if and only if the spectrum of the matrix A is included in this stability region, which is very well known for those researchers who deal with the stability analysis of systems of fractional differential equations with equal fractional orders. But this theorem also has a second statement, which tells us that the system, the linear system, will be stable if and only if the spectrum of the matrix is included in the closure of the set as Q defined above, and the eigenvalues of the matrix A, which satisfy that the absolute value of the argument is equal to Q pi over 2, so we are exactly on the boundary of the stability region as Q, have geometric multiplicity equal to 1. So when we were writing our review paper earlier this year, together with my former PhD student and Professor Garapa, we actually looked at several papers of Martinion, because what we wanted to do, we wanted to include a short proof for this theorem into our review paper, because we felt that in some way it would be like closer to a tutorial, or like for educational purposes, it would be nice to have a complete short proof included in our review paper. So when we were looking up Martinion's earlier results, we just came upon a very short sketch of the proof for this theorem, which was based on properties of the two-parameter Metagrapher function. And but it was actually this second point was not discussed, and unfortunately we were unable to find the original proof of Martinion regarding this second step. So the idea was that we tried to do the proof from scratch, and this is what we found. Actually, what I want to first introduce are just some very well-known notions about the index, the geometric multiplicity of an eigenvalue, just as a reminder and just to clarify what happened in our proof. So if we consider a general matrix A and we transform it to its Jordan normal form, okay, with a transformation given by the matrix P, which is non-singular. Here the blocks GK actually represent the Jordan blocks corresponding to some eigenvalue lambda K of the matrix, and obviously they are of this form. And then if we have the following definitions. The index of an eigenvalue is actually the size of the largest Jordan block associated to that eigenvalue. So if the index of the eigenvalue is 1, it means that all the Jordan blocks associated to our eigenvalue will have size equal to 1. On the other hand, the geometric multiplicity of lambda K is the total number of Jordan blocks associated to the eigenvalue lambda K in the Jordan normal form of the matrix A. And this means that if the geometric multiplicity of an eigenvalue is equal to 1, as stated in the original Martinion's theorem, it means that we will have only one Jordan block associated to that particular eigenvalue, but it doesn't say anything about the dimension of that block. And finally, I have also included here just for completeness, the definition of algebraic multiplicity, which is obviously the sum of all sizes, the sum of the sizes of all Jordan blocks associated to that particular eigenvalue. So what happened is that when we did our proof, actually we found out that we have to replace geometric multiplicity by the index in the formulation of the theorem, and I will shortly explain why in the next following slides. So actually, obviously, the first statement is perfectly fine. And actually, the first statement is the most important part of Martinion's theorem, because this is the most frequently used part of the theorem. This limit case is just seldom used. But in any case, we believe that we managed to in some way to improve the formulation of the theorem, and the results have been published in this review paper earlier this year. So I will now explain very shortly our proof. So what we did is actually just transform our linear system to its equivalent form, where we have the Jordan normal form of the matrix A. This can be done by simply transforming, by using this simple transformation. Then we applied the Laplace transform to this linear system, and we deduced that the Laplace transform of the solution can be expressed in this way. And now, since J is the Jordan normal form of our original matrix, and it is actually a block diagonal matrix, we can find that the matrix, the inverse of the matrix S to Q times I minus J, is an upper triangular, is made up of blocks which are upper triangular matrices of this form. So here the entries are actually some negative powers of the terms S to Q minus lambda K. And the dimension of this block K is actually denoted by dk, and dk is exactly the dimension of the case Jordan block JK in the Jordan normal form of the matrix A. So with this observation, actually we are able to compute the Laplace transform of our solution. This is made up of blocks of size dk, which are of the following form. So we have the block capital ZK of S given by this formula over here. So obviously we have here dk entries. What we can notice here is that all these functions that appear right here are Laplace transforms of Prabhakar kernels. So when we apply the inverse Laplace transform, we will obtain the kth block of the solution Z in this form, okay, involving the Prabhakar kernels, which are shown right here. And now we are nearly done, because now we will actually consider the asymptotic behavior of all these Prabhakar kernels which appear in the representation of the solution. And based on the previous results that I have shown you earlier in the earlier slides, we actually have these this representation for the asymptotic behavior as t goes to infinity. And from here we can observe the following important things. Well, first of all, if the argument of lambda in absolute value is larger than q pi over 2, then obviously we have this term going to 0 as t goes to infinity, and also so we will obtain that our solution will converge to 0 if all eigenvalues satisfy this condition. So we obtain basically the first part of Martinion's theorem, and also we obtain the fact that the solutions will converge to the origin as t to the power minus q. On the other hand, we also obtain the fact that if the absolute value of the argument is smaller than q pi over 2, strictly smaller, then this corresponding Prabhakar kernel will be unbounded, so we will have instability. And in the limit case, when, let's say, we have an eigenvalue of the matrix A, which satisfies that the absolute value of the argument is equal to q pi over 2, so we are exactly at the boundary of the stability region, what we may notice, so we are looking here at the first branch, what we may notice is that our Prabhakar kernel is going to be bounded if and only if this power m minus 1 is 0. So this means m is equal to 1, because in this special case, the exponential will be bounded. So what we obtain based on also the previous representation of our solution is that in this limit case, if we want bounded solutions, we need the dimension of this vector to be equal to 1. So dk is going to be equal to 1, which actually means that the dimension of the largest Jordan block corresponding to that eigenvalue has to be equal to 1, meaning that the index of the eigenvalue is equal to 1 and not its geometric multiplicity. So this is just a small detail that we wanted to slightly correct. And what I would like to show you are some numerical examples which have been done by Roberto Garapa, just to show that indeed this is the case. So for instance, we will consider first the linear system with fractional order 2/3 and the matrix A1 given in this form. We can see that in this case, the Jordan normal form is this one for the matrix A. So the eigenvalues are 1 plus minus I square root of 3. And actually we have, for each of the eigenvalues, we have exactly one Jordan normal block. Okay, this one and this one respectively. So the geometric multiplicity is going to be 1 for each of the eigenvalues, while the index is 2 because the dimension of the corresponding Jordan block is 2. So what happens here, according to our version of the theorem, is that indeed we won't have stability in the limit case. So the eigenvalues, naturally, they can be also expressed as the exponential of plus or minus q pi over 2 times I, where q is 2/3 in this case. And indeed, the numerical simulations show that the solutions do not converge to 0. They increase indefinitely. Actually, they oscillate and increase in absolute value as t goes to infinity. So in this case, actually the second statement of Martinion's theorem fails. I would also like to show you an example. Actually, it's a slight modification, if you notice, of the previous matrix. Instead of the matrix A1, we just remove this upper block here and replace it by the null block here. And now the Jordan normal form of the matrix is this. The eigenvalues are the same, but the difference is that we have 2 Jordan blocks corresponding to each of the eigenvalues. So the geometric multiplicity will be 2. But the index of each eigenvalue is going to be equal to 1 because the dimension of each Jordan block is equal to 1. And then now what we can also see based on the numerical simulation is that actually the system is going to be stable, the solutions are going to be bounded, and this agrees with the result that we have just presented in the theorem. Okay, I also have 2 more examples here in the case of asymptotic stability and instability, but these are very well-known results. So you can see here the matrix A3 is just a slight modification of the first matrix that I have considered, but on the main diagonal, instead of 1, I have 1 minus epsilon, and epsilon is going to be considered 0.1 for the numerical simulation. So now what happens is that the eigenvalues are in this form, and it can be simply shown that the arguments in absolute value are larger than q pi over 2. So we are in the asymptotic stability region when q is 2/3, and indeed the solutions will converge to 0. On the other hand, now we have a slight modification of the second matrix. And again, here on the main diagonal, instead of 1, we have considered 1 plus epsilon. Epsilon is the same as before. These are the eigenvalues, and we can simply show that they are in the instability region for Q equals to 2/3. And indeed, numerical simulations show that the solutions diverge from the null solution from the origin. So this is what I wanted to present today. Thank you very much for your attention, and also if you have any questions.
So may I ask some questions?
Sure.
Yes. So I have some comments. First of all, thank you very much for a very, very nice presentation.
Thank you.
Excellent result. My congratulations.
Thank you.
First question or comment is with respect to the Prabhakar function. As Virginia mentioned, it's really a very special case of the general right function. And I can imagine that some of the results that were derived for the general right function can be applied to derive the corresponding results for the Prabhakar function. In particular, with respect to the asymptotical behavior. Wright
Yes,
investigated in a series of papers, Wright investigated asymptotical behavior of the general right function. And my question would be if by derivation of the asymptotical formulas for the Prabhakar function, the results by Wright were used, or if the asymptotical representation for the
Yeah, so
Prabhakar
actually,
function were
I have
derived independently.
yes, actually, yeah, we rely on the work of Paris, which deals with right functions.
Okay.
Actually, back in 2020, yes, he have dealt with right functions, and yeah, he has studied asymptotic behavior for the right function, deducing from there what happens in the case of the Prabhakar function. So actually, these the results that we are using here are actually taken from the previous work of Paris, and also mentioned here in the survey paper of Professor Menardi and his group. But I'm sure that initially, yes.
Yeah, I'm aware of this paper by Professor Paris, but in fact, in this paper, he just made the asymptotical formulas derived by Wright more accurate. He took into account also some additional exponentially small terms. But the main results regarding the asymptotical behavior of the right function were really derived by Wright. So, I mean, the asymptotical behavior you showed us, of course, it can be found in the paper by Paris, but this asymptotical behavior was derived already by Wright.
Okay, okay. Thank you very much for the comment. Actually, yes. Yes, I have to mention that I'm by far not a specialist in special functions, so I am just using them as tools, and I really appreciate the comment. And yeah, so actually we have used the asymptotic behavior, so these properties of the Prabhakar function as a tool for our proof, and we were happy to go back to the papers of Professor Paris.
Yeah. Well, another question or comment is as follows. You mentioned that there is no analytical expression for the Laplace transform of the Prabhakar function known, but I'm wondering because in fact the Prabhakar function is a particular case of the right function, and for the right function, for the general right function, it's possible to derive a general formula for its Laplace transform. And thus,
okay, but maybe
in
not
my
a
opinion,
very
should be possible
simple
to derive a formula for the Laplace transform of the Prabhakar?
Yes. I'm not aware of a simple representation of the Laplace transform for the Prabhakar function, and in this way, for the Prabhakar kernel, actually we have a very simple representation for the Laplace transform. Is this one, which can also be observed once, we try to solve the linear fractional order systems with the equal order Caputo derivatives. So actually, this is this is what I meant, that there's not a simple analytical representation, so a simple formula. Of course, we can derive representations for the Laplace transform, but there's no simple analytical simple formula for that.
Yeah, you are completely true. I agree with you that for the Prabhakar kernel, we have a very simple representation for the Laplace transform, and the representation for the Laplace transform of the Prabhakar function will be for sure a very special function.
Functions, exactly. Yes.
Complicated function. Of course, it's possible to derive it, but
yes, of course, but not in a very simple analytical way. Exactly. Yeah. And also the Prabhakar kernel has also the advantage that it is used in the Prabhakar integral and the differential operators, and then in the there's a whole theory for fractional differential equations with the Prabhakar derivative as well.
Yeah, I think that the popularity of the Prabhakar function and Prabhakar transform is just in this simple formula for the Laplace transform. It's the reason for popularity of the Prabhakar theory nowadays.
Yeah, possibly true.
Yeah. Okay, thank you very much.
Thank you very much. Thank you very much for your comments.
Yeah, so thank you, Professor Iva Kaslik, for a wonderful
Thank you very
talk.
much again for the invitation. I will stop sharing.
Yeah.
Okay.
Yes.
Thank you.
So
Iva,
the next.
Thank you.
Thank you, Iva, ma'am, for your nice presentation.
Vediamo se riesco a farlo. Se il video, vediamo.
Yeah. So the next speaker will be Professor Francisco Menardi from Bologna University, and he's the creator and done very pivotal work, especially in these viscoelastic materials. His frequent visits to India and association with Professor Mathai. So they have really trained a large number of students in India, and these fractional calculus, fractional differential equations, and all these subjects are inculcated in Indian scenario. So it's a very, I would extend a warm welcome, especially to India. Professor Menardi, we really remember your our long association with Professor Mathai in Kerala. So welcome, and the dais is yours. Please, I invite you to start your lecture.
È andato via il... But I didn't find to share the screen. Eccolo qua. Share the screen. Provo. Ecco. Allora, vediamo un po'. Chat, document. Qui. View, PDF. View screen. Questo è il punto più critico.
Professor Menardi, you just stop this sharing because the LaTeX is visible now. I think You just
okay.
share the
Do
file.
you see,
First you,
do you
first
see my screen?
yeah, we can see you are sharing, but it is a LaTeX file.
We only see the source file.
It's
We are,
paused. Okay.
we are seeing the source file.
Lisa, do you see?
It's better you just stop sharing. First you open that PDF file and then you start sharing so that it will be visible.
So please open the PDF file on your screen.
Paused, perché paused?
Dice di aprire.
And then share the screen.
No, ma è qui? C'è? Non capisco. È qui? Speaker.
Devi aprire.
Sì, ma c'è qui, io lo vedo. Dici, your screen sharing is paused. Perché è paused? New share. Allora qual è? Questo, aspetta, questo. Ok? Is okay?
Yeah, it's okay.
Mi dici sì che si vede.
It is okay, it is okay.
Yeah,
It is
it's
visible.
okay.
Ah,
Yeah.
You make
finally,
it
I
full
was
screen if
successful.
possible. If
I was
possible.
successful because the connection is not so good. Anyway, I would like to thank the organizer to invite me. And I would like to say that this talk is practically based on a paper in preparation or submitted to publication, but with Professor Parish and also my former student Armando Consiglio. Then, apart the acknowledgement to you, to the invitation, I would like to remember also my thanks to the support of the journal Mathematics, because it was possible for me to edit three booklets. One, fractional calculus theory and application. The second is shared with my former student Giusti, advanced mathematical method. And the third, which is stopping now on the 3rd of December, part special function with application in mathematical physics. And in fact, you can see here the photo of the two booklets, which are available free in internet. The third booklet will be available, of course, next year. Then I would like to promote my books, of course, and my book devoted to waves in linear viscoelasticity, which was edited, published by World Scientific in more than 10 years ago, but I have prepared the second edition, which will be available next year, in spring, I presume. Of course, I would like to say to point out the book on Metagrapher function, my favorite function, which came from an idea of the late Professor Kilbas and shared also with Professor Gorenflo and Professor Rogozin. And unfortunately, Gorenflo died, but with the help of Rogozin, we are able to write the second edition, which is radio. It was published in last year. But I would like also to say, here are the booklets, the book, the photo of the book, but I would like to say something about my perspective book, which contains the lectures I give in my course for physics for more than 40 years, so that it contains also other topics, not only related to fractional calculus. Then I would like to thank again, it is typical for me to thank again mentors. Professor Caputo, who introduced me in the fractional calculus during my PhD thesis, it means many years ago, but in particular, Professor Gorenflo, with whom we share our love, if you can say, for Metagrapher function. In fact, I met him in Bordeaux in '94, and then from 95 up to 2015, we have collaborated. The photo is very old together in April 2002, when Caputo visited Bologna and Gorenflo the same, but many years ago, just like 20 years ago. Unfortunately, I lost Gorenflo guidance and collaboration in 2015 because he suffered strong health troubles and he died in October in 2017. Anyway, I would like to say that in a website devoted to fractional calculus and modeling, I put a document related to him because it was very important for me and for the development of fractional calculus. Now, the abstract of this paper is containing the right function of the second kind. I mean the classical right function, because these are related to probability theory and in practical in fractal diffusion process. In this paper, these functions are compared with the well-known Whittaker function, which Whittaker functions were introduced last century by Whittaker and are a special type of hypergeometric function. But anyway, it was occasion for me to check and correct two presentation in the literature. Okay, now this is the contents. After an introduction, we introduce a table of spatial evaluation of the right function in where they are expressed in terms of the Whittaker function, and then I recall in the third section the Laplace transform where the right function enter, and also my concept for students for the 3-4 systems. Anyway, I recall about the notation. The original notation of right is with 5, but then I prefer to call with W in honor of right. Unfortunately, also Whittaker has the same W, and I used italic W for Whittaker. The same problem came also for Metagrapher function, uses E. In fact, the same symbol is used for the exponential integral. But for fractional calculus, it's more important the Metagrapher function, which I define as the queen function of fractional calculus. So that we use W for right function, and this was also recalled by Virginia. Of course, Virginia is a specialist of multi-parameters functions. Instead, as a physicist, I prefer to work with 1, 2, at most 3 parameters. But in principle, we can get this function as a simple case of more general function. The series converge for lambda greater than -1 is very important, but we have to say that in the Batman project, it was only lambda greater than 0, so that probably for a misprint. So that when I introduced this function by myself, Professor Stankovic was able to say to me that was already made by Wright, but later on and not expressed in the Batman project, which was for me the only source. But this is also known as a modified Bessel function because in some case it reduced to Bessel function. And Bessel function, you know, are well known to everybody. Anyway, nowadays we have the NIST project, which is more modern, but nevertheless, Metagrapher function and right function are still treated in a very short way. I don't know why, probably because of prejudice against fractional calculus by the editors. Of course, I have to know that in spite now that fractional calculus has many papers, there are people who still are against. But it is natural. We know also the same problem for the vaccine. Now we have people who are no vax, so that people can say everything, and in spite of the majority of the population. Anyway, what is the reason to treat this function, or at least for me, was to generalize the diffusion equation to not integer order in the time. And of course, using the Caputo derivative, because for me, it was the starting point. And then I rediscovered the Riemann-Liouville. The same it was for Caputo. Anyway, this is another story. The function was termed the right function of the second kind when the lambda is negative. And in that time, it was the first year of 90, I independently, of course, because my source was only, and I repeat, the chapter 18 of the third volume of the Batman project, we can see that there are new the first parameters is always positive in their definition. Probably for image print, because then in the references they quote also the paper by Wright, but probably they did not read this. Anyway, these are the main functions, which are called by Podluni Menardi function, but of course are simple case, special case of the right function where the first parameter is negative. In that time, I have to give a name to this function, and in this I put my initial F and M. But F are important because in practice they are related to the stable distribution by Levy, were introduced in 1920. And this instead is important as a fundamental solution of the Cauchy problem of the fractional diffusion equation in time. And in fact, this function I prefer to call M right function because to keep the name of M. But in some case, they are related to simple function. For example, of course, for alpha, for nu 1/2 is R the Gaussian, which is very famous as in probability and sense. But for 1/3 for Airy, for 2/3 is related to Airy. And this was the inspiration to contact someone, expert of Whittaker function, Professor Paris, just to see, to explore if when the order is related to 1/3, if there are or 1/2 are related to Whittaker function, because also the Gaussian is a particular Whittaker function, and also Airy function. And this was the inspiration, the reason. Of course, as a physicist, I like to plot the function. For me, a function exists if it's plottable. I know that some experts of function are not interested to plot only to formula or only to theorem of existence and uniqueness. But as a physicist, I like to see the function. And in some sense, I am related to the late Professor Tricomi, was in practical my example in teaching. And it is very important to see the evolution of the m-right function, which is a particular case, I repeat, of the right function, when the order is negative, and also the argument is negative, and can be extended also in a symmetric wave, also for x positive, and for the other side. But anyway, I asked to my student, former student Consiglio, to plot in YouTube. If I have time, I can show you the evolution of the m-right function from 0 to 1, just to see the evolution of the fundamental solution of the diffusion equation when the order in time is between 0 to 1. And when is 1/2, we have the classical solution of the diffusion equation expressed in terms of the Gaussian. But when nu is 1, we have the 2 delta function, because we have the solution of the D'Alembert wave equation. And this excited me. But of course, other people deal this, like in Japan. Anyway, when the things are important, it is very difficult to be the first, because we have in the past a very good mathematician. I learned, just to say, someone told to me that if you go back to the results, we arrive to Eulero. And in fact, Eulero made a lot of things. Anyway, this is just to not have the prejudice about what's the first. Anyway, I repeat the notation. Phi is the notation used by Wright, and my notation, which is more common for infractional calculus. Yes, and what is the relation? We start from the Whittaker. Whittaker in 1903 introduced this function, which were not hypergeometric function in strict sense, and in fact it was the starting of the confluent hypergeometric function. And as a Bessel function, they satisfy a linear differential equation of the second order. Do you see? What do you say? Did you see? Yes. No. Do you see?
The wrong difference distance.
This is equation. This is equation of Whittaker, which depends on 2 parameters, and you see the solution are the so-called Whittaker function, and we have 2 integrals because it's a second order. Yes, and Whittaker noted that the equation, it remains unchanged if nu is replaced by minus nu, of course, because in square. But also if mu is replaced by minus mu, but if x is replaced by minus x. So that we have practically 4 functions. Then we have 2 linearly independent solutions, also Whittaker function, which I define in this way. mu nu x and mu minus mu nu minus x for x positive, because I prefer to work with positive x. But to see this, in fact, following my desire to see what happens in practice, my student Gonzilio was able to understand the difference, because at least according to Paris, according to NIST, because Paris was an author of NIST project, the Whittaker function have a branch cut like logarithmic in the negative real axis, so that if you compute the function in the branch cut, we have a complex value. And in fact, we get complex values using Mathematica or MATLAB. I have to say that I am not practice of Mathematica, which I used many years ago, but then I abandoned. But Paris used Mathematica, and Consiglio used MATLAB, and the same programs gave the same result. So that you see that if you like to have x greater than 0, we have to consider this part of the Whittaker function. Then, what we see in the literature? In the literature, I saw in the nice paper by Stankovic, which was, I met him in 94, and he was in 1970, he produced a nice paper on the right function with, which I call now second kind, but with first parameters negative. He said this formula, which is you see, related with Tucker function, right function with Whittaker function. But what happens? In this representation, now we have seen that x is negative. The argument is negative, and this it seems to be a definition not compatible with the definition which we know that Whittaker function has a branch cut in the negative argument, so that cannot have a real value. For this, I was related, I contacted Paris, because Paris and Vinogradov, they have related for a simple case of a right function of the second kind with a Whittaker function with positive. So that I say this Professor Paris is my author to complete my project, to see a general relation between right function and Whittaker function, because these are simple cases of my project. And in fact, you see the function is plottable, and the two, one is a Whittaker, this one, this is a right, and my student was able to see that check with a plot, because the plot are the same, because you see, mathematician can write the formula, but the formula should be checked. And what is the way to check it? Numerically, and numerically with plots, because if the plot coincide, it, of course, is not a proof, but at least is a necessary condition that the truth is achieved. Okay, so that now we tried to say what is the right connection to correct the Stankovic expression. And this is now our expression, and it was checked the first member and the second member are equal, as you can check from these plots. Of course, you cannot see the same, but coincide exactly. Then, okay. Now, what is a table? Well, the table to relate the Whittaker function, the right function with the Whittaker function. Now Whittaker function are defined as two symbols, M and W. Same M and V are similar to my symbol, so that for right Whittaker function, I used italic letters. This was a problem. The special functions are so many, and it is simple to see. It is very natural to see the identity of symbols. Anyway, here you see the method of proof was given in an appendix. And here I give you only the relation, and this relation was given, you see, by Paris, which was able to see that when nu is rational, 1/2, cioè a multiple of 1/2 or a multiple of 1/3, yes, our conjecture was satisfied. And in fact, it is possible to find this relation. Of course, for me, it was a very important result. And the proof are in appendix. Of course, for nu equal 1/2, instead, you can get, for example, the Gaussian. Here we get the integral of the Gaussian, but anyway, the same. And then we can go. Okay, 1/3, you see, you can able to find the relation with the Airy function. So that, but of course, this is only when nu is 1/2, 1/3, or 1/4, and so on. You can see here. Let me see now. I lost my. No. Contents. Sorry. Ecco. Now, what is the inspiration? The inspiration came also from the paper by Stankovic, which who was able to relate the Laplace transform of this inversion. The inversion is Laplace transform, because this inversion is very important to solve the fractional diffusion equation in time, the Cauchy problem. And of course, Stankovic gave a rigorous proof. Instead, as a physicist, I gave a simple proof, and indirectly, I discovered that also in 1973-74, with Peter Buchen, for another topic, we arrived in the same result, but we were not aware of the existence of the right function. Unfortunately, the right function are by many authors disregarded because they see are cumbersome. Instead, I have to say the special functions are like the notes in music, do, re, mi, fa, sol. Every paper in applied mathematics can use the special function. So that special function have to be taught in courses, at least up to 2 parameters. I don't say up to n parameters as Kiriakov Yes, it's only for PhD students, but students should use not only the Bessel function or the gamma function, but also the Metagrapher and the right function, because are simple, not difficult, because are related to this inverse Laplace transform. And this Laplace transform are known, at least when I considered, only when u was 1/2. Why? Because people consider only the diffusion equation. But if you like to generalize the diffusion equation, we have to consider nu different from 1/2. And this was my desire. It was a simple exercise which I could give to my students in '93. But the paper was rejected because, say, the referee, every people can solve simple equation and gives the solution. And this is not mathematical physics. Yes, I saw this is simple, but before this idea was not used, at least as no, I cannot find any table where nu is different from 1/2, so that I was obliged to make my table. But of course, I discovered that this topic was also considered before Stankovic, of course, but only from a mathematical point of view, not for the application of the fractional diffusion equation. Of course, fractional diffusion equation nowadays is on fashion, but you have to think in 90. In 90, nobody. People laugh from my paper of 71 up to 90. They laugh when they listen someone speak about fractional calculus. It's like a fashion, like a marathon, if you like to make a comparison. Anyway, I don't like to be aggressive for this, but I am a little bit astonished about the fashion. Why fashion? If the mathematical is good, is not fashion, is mathematics. And application in physics can be found sooner or later. And anomalous diffusion, for example, now someone told anomalous diffusion is normal. Okay, probably. Okay, now the proof of this simple relation, I repeat, this one, for mu greater than 0 and nu between 0 and 1, yes, this is given by right function. So that because this should be simple to be available in, but if you look in the table of Laplace transform, you don't find this. Only when mu is 1, 1/2, and nu is 1/2. Of course, when u equal 1, of course, this delta function, which are not a simple function, but nevertheless is already used in the table with function, generalized function. Okay, now I would like to see what is in the literature. In the literature, I say when u equal 1/2, we have, for example, the book by Deutsch, which is the Bible of the Laplace transform. You see three functions, which I call to my student, with three sisters, because known one, you can get the other one. Yes, and these functions are simple case. Oh, terrible. Now they change. I don't know why they change. I don't know what I did. You see? No, they move, you know, I try to get again, come si fa a voltare? I don't know why it turns out.
Professor Menardi, your view may be, you may have, yeah, it is fine now. It's fine
Yes,
now.
yes. I don't know why the computer change, but anyway, I go back again. I hope so. Yes, yes, yes. Sorry, but at my age is very normal. Yes, okay. I got the three sisters, okay? The three sisters are simple case of the right function where the first parameters is 1/2 and the second is 1, 0. Okay, the three sisters are here expressed in terms of x and t. As a physicist, I have to plot the function. I'm sorry for people who don't like plots, like the editor of integral transform and special function, but I don't understand this kind of mathematician. If you like apply mathematics, we have to see the function, at least when the parameters are only 1 and 2, and the variable is space and times. Of course, I don't speak about space-time domain in 4 dimensions, you know. I work in 1 dimension, which are good for students, for people who can then change and make a Nobel Prize later. Okay, just to be polemic. Anyway, so that for me it was very easy to generalize the 3 sisters in 4 sisters, because 4 sisters, it means when nu is different from 1/2, 1 minus nu and nu is different, because when nu is 1/2 are only 3. And these 3 functions became 4 functions and are plotted by my student with MATLAB versus x versus t.
Professor Menardi, just 5 minutes are left.
Yes, and now I would like to say the last formula. Humbert, who was able to treat an equation of this kind? Humbert in 1945, during the war, yes, during the war, was interested to invert this function, but he gives this expression without proof. I have the paper and no proof of this. And the same question of Stankovic. You see a Whittaker function with negative argument. And this gives a complex, at least according to mathematics and MATLAB, this gives a complex number, so that it cannot be the inverse Laplace transform of a real function, which is this one. Okay, so that we were able to correct this error and obtain this. And this is the plot, which prove again that our solution is correct the result by Humbert. Unfortunately, Humbert and Stankovic are died, so that I cannot discuss with them. This is the only problem we have. But nevertheless, we can say that we have checked this formula and probably correct their form. Okay, there I thank you, because I don't say the appendix, because the appendix can be available in the archive, and this paper is so that is free, downloadable for everybody, and in future I hope so it will publish it in a journal. We have submitted, and we know now we have to await the reply of the referees, of course. Thank you very much again.
Yeah, thank you very much, Professor Menardi, and your ramblings in we take this function. So thank you very much. Are there any questions?
Professor Menardi, if I am not mistaken, the right functions arguments that are not real positives when you consider that alpha and beta is suppose alpha and beta, and is that not real positives? In suppose for a reference, you can take that equation 3.1, which you were suggesting. In your slides, the 3.1 equation 3.1. This previous
no,
one.
Point 1. Allora,
3.1.
if I have time, I can show the plot of the YouTube. If you go in YouTube, and look for M simulation of M right function, you see in YouTube the simulation by Consiglio where the M right function, with a particular case of the right function, I repeat, changing from the exponential to delta function, to do delta function. So that I probably did not understood your question because unfortunately my English is poor and in computer is more poor again. And but you see that the case of nu equal 1, the right function is no longer entire and is related to delta function. And the delta function is not potable. I hope to have replied to your question. In any case, you can write to me your question so that I can understand better.
I will write to you. I will write to you, sir. It's okay. Thank you very much for your session.
Thank you very much.
Adesso che ti contatto.
Sì, questo ho capito. Vediamo. I partecipanti sono 62, sono aumentati.
Bene.
Adesso vediamo che c'è Ballecar e poi dopo c'è la Gigi.
Allora ti fermi a mangiare.
Professor Varsha, she is not there. Professor Varsha?
She is not there actually. Dilip is not there. Next speaker is Sachin actually. Sachin Bhatt.
Yeah, I think she had some connection problem. Sachin sir, you can start sharing. Meantime, she will join.
Okay, sir. Is the
Yes,
screen visible?
yes.
Okay.
Yes, ma'am. Yes. Yes.
So,
Yes. Okay, ma'am. Okay. You. Okay.
So in this talk, we discuss how Metagrapher functions are used in analyzing fractional differential equations. So we take a brief review of composition rules of Caputo fractional derivatives and the general solutions of linear systems. And then we present the proper ways to convert a single fractional differential equation to a system of fractional differential equations of lower order. So basically we use the properties of Metagrapher functions, their Laplace transform, and so on. So motivation, first thing is if we consider integer order, positive integer order derivatives, then all these things are very easy. I mean, composition is trivial thing, but it is not the case with fractional derivatives in general. Second thing is if we consider such single equation which is linear, higher order, containing higher order derivatives, then we can split it to a system of differential equations with first order derivative in each equation. Okay, so such splitting is trivial when we consider ordinary differential equations, but this is not trivial when we consider fractional differential equation. Okay. So these are the basic definitions. I am not going in details. So throughout this lecture, I will consider Caputo fractional derivative. This is, as usual, Metagrapher function. One parameter, then two parameter, and this is multi-parameter Metagrapher function where we have multinomial coefficient, and these are appearing as solutions of fractional differential equations containing more than one derivatives, or we can call this as multi-term fractional differential equations. So Laplace transform of fractional derivative. When we consider alpha order derivative and alpha is between integers n-1 and n, then it is s raised to alpha, capital F of s, capital F is transform of function f of t minus summation s raised to alpha minus k minus 1, kth derivative of f at 0, k from 0 to n-1. If we consider this equation, linear differential equation, d alpha x of t equal to d alpha x of t plus lambda x of t equal to 0, and we take alpha between 0 and 1, then the solution is given in terms of Metagrapher function, and it is x of 0 e alpha minus lambda t raised to alpha. Here we can see one property. We can compose fractional derivative with integer order derivative like this: d alpha dm f of t equal to d alpha plus m f of t, but it is not in general equal to dm d alpha f of t. Okay, here m is natural number, alpha is non-integer. Then next result is, if x of t is m times continuously differentiable function on this interval 0t and alpha between m-1 and m, then alpha order derivative of x evaluated at t equal to 0 is 0. If x of t is c1 in this interval 0t, then d alpha 2 d alpha 1 x of t is same as d alpha 1 d alpha 2 x of t, and that is also same as d alpha 1 plus alpha 2 x of t, where alpha 1 and alpha 2 are satisfying this condition. Means if the sum of these two orders is less than or equal to 1, then we can have this result. Generalization is to this result is given in this theorem. In earlier case, our function was c1. Now we consider ck function, and we consider alpha and epsilon positive. Then there exists some L natural number and k which is greater equal L, and such that this alpha plus epsilon is in this interval L-1 to L. Then we can compose this. We can write d epsilon d alpha f of t is same as d alpha plus epsilon f of t. Okay, so these were basic results given in the literature. Now question is, can we use composition rule while analyzing fractional differential equation? Okay, so we consider this classical system, means with derivative 1 x dot equal to f of x, and as usual this function is c1. If x of t is solution of this equation starting at point x0 defined on interval I, then this function is c2 function. Okay, however, in 10, if we replace the classical derivative by fractional derivative, then the solution is not even continuously differentiable. Okay, so these are some differences between classical thing and fractional thing. Now the solution of this equation d alpha x of t equal to lambda x of t is not continuously differentiable at t equal to 0. Okay, so if we consider integer order derivative, then this solution is C2 function. But for fractional order, it is not even C1. Okay, so it is not C1 at point t equal to 0. So solution is this given in terms of Metagrapher function e alpha lambda t raised to alpha. And if we expand this series, then we can see that the derivative of this function evaluated at t equal to 0 will not be continuous at t equal to 0 because of this term t raised to alpha minus 1. Alpha is between 0 and 1, so this will be in the denominator. So this theorem shows that this solution of fractional differential equation does not satisfy the condition in theorem 4.5. 4.5 means this one. If the function is continuously differentiable, then under this condition alpha 1 plus alpha 2 less equal 1, we can have such a nice result. Okay, but Metagrapher function is not satisfying this condition, so we cannot expect such thing. D alpha 1, D alpha 2 of Metagrapher function is not equal to D alpha 1 plus alpha in general. Okay, so here we see one example. So we take alpha 1 to be 1 upon 4, alpha 2 is same as alpha 1, and we take Metagrapher function e 1 by 4 lambda t raised to 1 by 4. So we obtain this as lambda square e 1 by 4 lambda t raised to 1 by 4. And if we take summation of these two things, means alpha 1 plus alpha 2 is now 1/2. Okay, so if we consider this as d alpha 1 plus alpha 2 and this function, then we obtain different thing. Okay, so these are not matching. So such weird things can happen with Metagrapher function. So question is, can we split fractional differential equation into system of lower order fractional differential equations? Okay, so since we have seen in general we cannot compose such things, we cannot add the orders of derivatives when we are taking derivative of Metagrapher function. So since the result is not true in general, can we have some result? Can we have some condition under which we can apply such rule? So here is that rule. We take alpha 1 positive, alpha 2 positive, and the number alpha is such that 0 less than alpha 1 plus alpha 2 less equal alpha less than 1. Okay, so all these are between 0 and 1. If we take such thing, then Metagrapher function e alpha lambda t to alpha. Okay, so this index alpha, which we are taking in the definition of Metagrapher function, this should be greater than or equal to sum of these two orders. So condition is this alpha should be greater than or equal to alpha 1 plus alpha 2. Then we can write d alpha 1, d alpha 2, e alpha lambda t raised to alpha is same as d alpha 1 plus alpha 2 e alpha lambda t raised to alpha, and it is again same as d alpha 2 d alpha 1, okay, of the same function. And this is true even though this function is not continuously differentiable at t equal to 0. Okay, so in the literature, result is if the function is continuously differentiable, then we can do this. Okay, so this is sufficient condition but not necessary. Okay, so counter example is often using Metagrapher function, and condition is provided by this result. Proof is trivial. We just have to use the properties of Caputo fractional derivative and this series. Okay. If we consider alpha 1 plus alpha 2 greater than alpha, means if we consider smaller values of alpha, then above theorem need not hold, and we can verify with any examples. Okay, so this is the example. If we take alpha 1 1/2, alpha 2 1/2, so alpha 1 plus alpha 2 is equal to 1, but we are taking alpha to be 1/2. Okay, so this alpha is smaller than alpha 1 plus alpha 2, and we are not getting the required result. Okay, so composition is not true. And these are some more examples. Now, this was first problem. Second problem is equivalence between fractional differential equation and system of lower fractional order differential equations. And here we use the Metagrapher functions and check the possibilities of such equivalence. Okay, so we consider this d alpha x of t equal to lambda x of t. Solution is given in this form. If alpha 1 plus alpha 2 equal to alpha, and if we could write, okay, so we in some cases we use proof by contradiction. If we could write d alpha 2 d alpha 1 x of t equal to lambda x of t, then this is equivalent to, okay, I mean, if we could split this, then we will be able to write d alpha 1 x of t equal to certain function, say y of t, and then d alpha 2 y of t equal to right hand side. Okay, so splitting is like this. Okay, so we take sum alpha 1 plus alpha 2 equal to alpha, and then we consider this equation. If splitting is allowed, then this 21 should be same as 22. The second equation can be written as d alpha minus alpha 1. Okay. If this is true, then we can proceed. Let us take Laplace transform. Laplace transform will give this equation. So it gives capital X of s equal to x of 0, s raised to alpha minus 1 divided by s raised to alpha minus lambda plus y of 0 into s raised to alpha minus alpha 1 minus 1 divided by s raised to alpha minus lambda. And inverse Laplace transform provides this solution. Now, y of 0 is nothing but, what is our y? Y is nothing but d alpha 1 x of t. So y of 0 should be d alpha d alpha 1 x at t equal to 0. And this is 0, and the solution is required. Okay, so here we are able to prove the equivalence. Okay. So 19 is equivalent to 22. That means we can split those things. Now next we consider linear two-term fractional differential equation, where we consider two derivatives. One is of order alpha, another is of beta. Beta is between 0 and 1, alpha is between 1 and Laplace transform of this equation gives Laplace transform of x of s given by this equation 26. Now we split and take the Laplace transform. Okay, so this is our solution using routine methods. Now we split that equation and take the system like this, means we call d beta x of t equal to y of t in this equation. So this is our y of t, and so d alpha x of t equal to minus a2 x of t minus a1 y of t. Okay, so this is our splitted system, and alpha is between 1 and 2. So it is of this form: 1 plus delta, where delta is between 0 and 1. And then there are different sub cases. First sub case is now our delta and beta both are between 0 and 1. So these are two possibilities. First possibility is beta is less than delta. Okay, that means alpha minus, here alpha minus beta is between 1 and 2. Now Laplace transform gives capital X of S equal to this equation given by 29. Now earlier we are having equation 26 as Laplace transform of this equation. Okay, so from the given system we obtain capital X of S by as 26, and here we are getting it as 29. Okay, so the equations equation 25 and the system 28, these two are equivalent if and only these Laplace transforms will match. And if we compare these two equations, we obtain equation of this form. Now our beta is between 0 and 1, so this cannot be true. Equation 30 cannot be true. So such splitting is not allowed. So our result is equation 25 is not equivalent to 28. Means simply calling this as y and splitting in the system 28 is not allowed in this case. Okay. So this is possible using Laplace transform and properties of Metagrapher function. So here we have taken beta between 0 and 1. Let us consider next case. Our beta was less than delta in first case. In second case, we take beta
Sachin,
greater than
5 minutes. 5
Okay.
minutes.
So in another case also, we arrive to contradiction and it is not possible. Okay. So in some cases, we have seen that we cannot split such things. So can we split such equation into lower order derivatives? So what are proper ways? So here we can split like this. First equation we take as d beta x of t equal to y1 of t. Then we write next equation as d1 minus beta y1 of t equal to y2 of t, and third equation as d alpha minus 1 y2 of t equal to minus a2 x of t minus a1 y1 of t. Okay, so instead of two equations, if we split it to three equations with these initial conditions, then we can check using Laplace transform that these two are equivalent. And we can have general result also, means we can have such m number of fractional derivatives involved in the equation, and we have this result proper way to split. So we need 2m minus 1 equations in this system when we have m number of fractional derivatives. Okay, and less than this number will not be useful. Okay, so computations are involved and some counter examples. So any system with equations more than 2m minus 1 will be okay in this splitting. If we consider equations less than 2m minus 1, then it will not work. Okay, I think I should stop here. Thank you.
Sachin, thank you for very interesting talk. Because of shortage of time, but we will allow a question. If there is any question from the audience, please. Okay, if there is no question, let us thank the speaker for a very interesting talk.
Thank you, madam, for inviting me.
Yeah, it's our pleasure. Okay, so now let's move on to the next speaker, which is myself only. So I think I should start sharing the screen. So is my screen visible?
Yes, yes, ma'am.
Yes, madam.
Okay, so my topic today that I have taken is Metagrapher function and in fractional differential equations. So much is said about Metagrapher function, so which was introduced by Metagrapher in 1903. And when he introduced, he only studied this from a very mathematical viewpoint as an academic study, and its relation to fractional calculus or fractional differential equations was nowhere in seen. Biman introduced a generalization in 1905, and Agarwal rediscovered this in 1953. And around 2000 or maybe 1990 onwards, its close relation with solution of fractional differential equation became very apparent, and now it is a very widespread use. So Metagrapher functions have attracted a lot of interest, and as in a book of Professor Menardi, they say that we like to refer the classical Metagrapher function as queen of fractional calculus, and consider all the related functions as her court. So these functions are playing now so much of pivotal role in fractional differential equations. So here we just enlist important properties that two parameter Metagrapher functions are entire functions. And another, this property is very I should say has profound implications, namely, except for e to the power z, which is e1 comma 1, other Metagrapher functions have infinity of zeros in the complex plane. So this is where actually many phenomena that take place with ordinary dynamical systems, they don't carry over to fractional dynamical system, and this property plays pivotal role in that. And secondly, the arguments of zeros of alpha comma 1 approach alpha pi by 2 asymptotically. Third property is the semi-group property. So Metagrapher functions don't obey semi-group property. This is yet another important point where the dynamics goes sort of goes wrong, you can say. The semi-group property is not there. So the dynamics that takes place in fractional order dynamical systems is rather very different. And the concept of flow of a differential equation, which is there in ordinary differential equation, is not carried forward. So these are some of the features. Now here, those who don't know much about fractional calculus, I'm just for the sake of record writing down these basic definitions. That Riemann-Liouville definition of fractional integral can be viewed as a generalization of Cauchy's formula, and this is given in expression 1. And Riemann-Liouville fractional derivative and Caputo fractional. So there are large number of inequivalent derivatives, fractional derivatives, but Riemann-Liouville fractional derivative and Caputo fractional derivative are most, I should say, popular and basic derivatives. So I have just, for the sake of completeness, I am giving here the definition. So here you first consider nth order derivative, and this you take dn minus q. So fractional derivative. In this case, you first take this integral followed by a derivative. Now, in today's talk, I'm trying to show where all places fractional as a solutions of fractional differential equations, Metagrapher function and its generalizations occur. So the simple example that first I give, so it is given in our paper with my student Sangeeta Chaudhary. So consider this non-linear equation with periodic boundary condition u0 is equal to ut, which is equivalent to fractional integral equation given in 5, where this is the Green's function, and the Green's function given has this solution. So you can see here how many places the Metagrapher function is appearing. Now, just to give an idea how the generalizations occur, let me so is this paper, can the audience view the paper?
Yes, madam.
So here what we have done is we have considered a more end situation. So here LD, so LD is the multi-term combination, alpha 1, alpha 2, alpha n, and here we are considering 3.2 and 3.3 periodic and anti-periodic boundary conditions. So you will similar lines get a generalization. So this is a one-term generalization, and then when you generalize for higher terms, this is the solution for the LD case, where this is a multi-term combination, and the Green's function is this much, where you have, this is a Metagrapher function with all these generalized Metagrapher function. And so the differential equation looks so innocent, but its solution has this Green's function, which takes pages of things. And this is whole paper. If I just browse through, one can see there's a lot of calculation. But interestingly, once you get a hang of this, then you yourself realize what will, but how to generalize this and get that correct Metagrapher function. Okay, so let me get back to my slide. Now, for the study of system of linear equations, one introduces a generalization of Metagrapher function for matrix arguments. So here, instead of argument x, where x is a real number, we consider A as a n cross n real matrix. And you can show that in this norm, this series is convergent. So this converges for all real A's, real matrices, and they are important as solutions of systems of fractional differential equations. So here in our paper in JMA, we have given a proof that if A is a n cross n real matrix, then this initial value problem d alpha a ax, where A is a matrix and x is an element in Rn. So this is a system of n equations, linear system, and it has a unique solution x of t, where this is E alpha comma 1 with this matrix argument. So this is where the whole study started. So Dethelm and Ford have investigated this equation d alpha y minus y0. In 2002, their paper has appeared in JMA. And in 2004, with my student, we have worked out its generalization to systems. And there again, if you consider this is a system of n equations, now we also consider for a Caputo case. So in the literature, we thought there is no particular discussion of Caputo fractional order differential equations. So we consider a system of Caputo fraction system of equations with Caputo fractional derivatives alpha I going from 1 to n. So this is a system of n equations with n initial conditions, which is equivalent to n Volterra integral equations. So we give this existence theorem. So the solution exists on this domain. And the interesting thing is, consider the equation and vary the initial conditions. And then we see the behavior of the solution. Then the behavior of the solution is bounded by this constant initial decided by the initial constant. And here again, the Metagrapher parameter comes. So one can see in how many directions Metagrapher function and its derivatives and its variants play a profound role in all this study. Another thing is the multi-parameter Metagrapher function. So it was multi-parameter Metagrapher function for real arguments was introduced by Hadid and Luchko in 1996. So where this is a known kind of popular extension. Now we generalize this, and we have given in our paper in JMA in 2005, we generalized it to matrix arguments. And for matrix arguments, if you write down this expression, then the generalization for matrix argument turns out to be this. So here only one term is the product of term, then product of m terms, and finally m going from 1 to infinity. And here all these alpha is this, they appear here. So this is a generalization of Hadid and Luchko series to matrix arguments. Now this is not just academic exercise. It interestingly, in this paper, what we observe, if you consider a system of equations where alpha bar is having this variable argument,
There is some network problem. She will join soon. Ma'am, you can share again. Ma'am, please share your screen. Yeah, it is visible. It is visible. Your mic is off, ma'am. Your mic is off.
hello, where should I start? I mean, when it went off, can you tell me? Is this generalization? So I think
After that.
After multi-parameter.
Yes,
Okay.
yes.
So this is where this is the generalization for matrix arguments. And very interestingly, one can see that this fits in when I consider such kind of system. Its solution, when I try to find out, this system of equations is equivalent to this system of integral equations. And I was described the decomposition method, which is valid for any such functional equation of the form u is equal to f plus lu plus nu, where L is a linear operator of its argument, n is a non-linear operator, and f is a known function. So I've just briefly described this, that then u is equal to summation ui, and then linear, because of linearity, L of summation is summation of L. And in this paper with my student Hussein Jafri, we have given this decomposition of the nonlinear operator as follows: n of summation ui is nu naught, and this addition and subtraction. And with this, we set up the recurrence relation. So I briefly browse through this. So this is a technique that we have developed. Using this recurrence relation, and the decomposition method yields these terms. So when I compile these terms, this addition gives us the solution. And very interestingly, that this solution is having this form. It is a multi-parameter, multi-term, multi-parameter Metagrapher function with these matrix arguments, where x alpha 1 a1. So a1 is nothing but obtained by, consider a, the a is this a. So a is this matrix. So a1 is consider first row, put all other zeros. A2 is put second row, take only second row, put all other rows 0. So that is the way. So this a1, a2, an, where ai is the only non-zero row, and ith row is ai1, ai2, ain. And so this is the very interesting solution which is obtained by the decomposition method. Now, thirdly, here is again, if you consider this equation, so where now you have mu k0 is ck, k going from m minus 1, mu is lying between m minus 1 and m. In that case, you see that the solution that you get is again in terms of such Metagrapher function. Now, if you consider the initial value problem and have the multi-terms, so actually when you have multi-ordered combination, you will get multi-term Metagrapher function. So the multi-term fractional differential equations and multi-term Metagrapher multi-term Metagrapher functions, they have very nice connections with each other. Now, with Sachin Bhalekar, we have found solutions of boundary value problems for multi-term fractional boundary value problems. So again there, so I will just share that briefly. So this paper appeared in 2008, where again, whenever we consider interesting solutions, interesting initial value problems, so here all these series have appeared. So if I consider a multi-term homogeneous fractional boundary value problem with this boundary condition and apply our methods, it nicely gives us various variants of Metagrapher series. So in these various conditions, and you will get different Metagrapher series. So it beautifully builds that series, pops up when you do all those substitutions. So this paper is full of variants of Metagrapher function. So now finally, so with this, I just wanted to the non-experts in this field highlight this point, that study of fractional differential equations almost boils down to study of Metagrapher function and their properties and their variants. Now, incidentally, very recently in our research in fractional dynamics, we are getting relations between fractional dynamics and zeros of Metagrapher functions. So here, let me just again revise the theorem that when you consider this system of equations, x dot equal to ax, where x is a vector, then the global existence and uniqueness theorem tells you that the solution E alpha T alpha A x naught is the unique solution of that initial value problem. And that what is a trajectory? So now we think of it as a dynamical system, because when alpha is equal to 1, we have x dot is equal to ax, and that dynamical system is thoroughly studied. And nonlinear dynamics is a branch of physics, and nonlinear dynamics, chaos control is a vast area of research done in ordinary dynamics. So our group has worked on its fractional version. In that study, now I will just highlight some interesting facts that we have come across or we have proved. So the trajectory we define as the set UTX naught, where xt, where t greater equal to 0. So we consider this and put t greater equal 0, the set of all such points is the trajectory of the initial value 4. So let me just highlight equation 4. So we are now studying this equation. Sorry, no, we are now considering x dot is equal to x. So I should say equation 7, sorry. So this equation, T alpha x is equal to x. So it should be equation 7, I'm sorry. That 4, not 4. So that dynamic. Now, intersection of trajectories. So when you will say two trajectories intersect, so trajectory UTX naught and UTY naught of 7 here, sorry, it is not 4, are said to intersect at a point P if there exists T and T prime such that UTX naught is equal to U tilde. So this is the initial condition x naught. It evolves for T parameter distance, and this is initial point is Y naught. It evolves T tilde parameter distance. And if it is equal, then we say these two trajectories intersect. Intuitive definition. Now, let us see how it is related to the eigenvalues of the Metagrapher function. So for that, we just note it, a small proof is required, which I am not given. An eigenvalue of E alpha beta of this matrix T alpha A. So this is also a matrix. So the an eigenvalue of this matrix is of the form E alpha comma beta T alpha lambda. So here, this is of this form. So this is T is capital T is a real number, lambda is a real number. So this is a real number. But interesting to note that an eigenvalue of this matrix is of this form, E alpha comma beta T alpha lambda. Secondly, as I mentioned in my earlier part of this lecture, that Metagrapher functions can have zeros. So exponential function which occur in ordinary differential equations, they don't have zeros, but Metagrapher functions have zeros, and that plays crucial role in the dynamics. And so the matrix E alpha T alpha A is invertible if and only if argument of lambda is not equal to argument of xi alpha, where xi alpha, which is complex, which belongs to complex numbers, is a zero of Metagrapher function E alpha z, and lambda is an eigenvalue of A. So the zeros of this matrix are related to the zeros of the Metagrapher function E alpha z. Now comes the interesting story of intersection of trajectories in fractional systems. So let us just see in the literature, you see that Kaslik and Sivasundaram in this paper, Neural Networks, have proved that except for the constant solutions, there are no periodic solutions of class C1 for fractional systems. So you do not get exact periodic solutions, although fractional systems can have limit cycle behavior for whenever argument of lambda is greater than or equal to alpha pi by 2, or for those eigenvalues which now actually in Iva Kaslik's lecture which she gave just now might modify this argument, maybe index or something will come here. So that with that small modification, this is the result. Now in integer order dynamical systems, two trajectories do not intersect each other in finite time. So this is where now the situation will differ. So it has been noted that fractional systems do not share this property. And Dithel et al. Have studied the intersection of trajectories for fractional systems and shown that in case of one-dimensional fractional systems, two distinct trajectories do not intersect each other at the same time. And this result is known as separation theorem for fractional systems. They also have observed that fractional trajectories can intersect at each other at different times because of their inherent non-local nature. So we have taken up this study further, and with my student Ameya Deshpande, we have shown in this paper, which has appeared in Chaos, that unlike trajectories of integer order dynamical systems, fractional trajectories can have irregular self-intersections such as cusp or node. So when you consider, so this is something which is very fundamentally different that is happening in fractional order dynamical systems. And the onus goes to the fact that the Metagrapher function can vanish at points in the complex plane. And in ordinary systems, the solution is related to the exponentials, where exponentials do not vanish. Therefore, there are no intersections. So this work brings out new connections between zeros of Metagrapher function and intersections of fractional trajectories. Now let us briefly look at the example. So let me just put on record the formal definition. So a regular parameterized curve is continuously differentiable map from I to Rn. So we are in n-dimensional situation. And when you say continuous curve, when it is regular, the total derivative is not zero. And a fractional trajectory is said to be regular if x prime t, so x prime means dc dt, is not zero for all t. Now a non-constant trajectory xt of this initial value 7, it should be 7, is regular if and only if each eigenvalue lambda of A satisfies this property. Argument lambda is not equal to argument eta alpha, where eta alpha is a zero of E alpha. That means in certain cases, you can have, whenever you have argument of lambda is equal to argument of eta lambda, you will have irregular solutions. And here we are giving an example. So we have constructed this example where we take alpha is 1/3 and take a matrix having these eigenvalues with the zeros of E alpha comma 0, and construct this matrix and substitute and plot the trajectories of these dynamical system. And here are the plots. So you get such kind of solution. It is a case of self-intersection, and x2t shows the cusp. So you can see that this can be a solution of a fractional differential equation. In the ordinary case, if you have such points, such a curve cannot be a solution of a ODE, but it is very interesting to see such a solution, such a curve is a solution of FDE. And the onus goes to the zeros of Metagrapher function. So these are the new connections, and that is where we have some interesting things to tell. So with this, I just project the references. So this is a book by Menardi. I forgot one, Kilbas, Gorenflo, and Rogozin. Name is, sorry for the mistake. So this is a book, Metagrapher function properties and applications, and very interesting, useful book we have used. Then these are the list of our papers where we have done the analysis of systems, system of fractional differential equations, non-autonomous with Caputo derivative, and Adomian decomposition, new iterative method, using which we have solved a very large number of examples and obtained the variants of Metagrapher functions as solutions of fractional equations, fractional boundary value problems, multi-term fractional equations, systems of fractional equations. And finally, this is the paper where we studied analysis of intersections of trajectories of systems of linear fractional, so which has appeared in. So with this, I stop here, and if there are any questions, I would like to address.
Can I ask you questions?
Yeah.
Yes. I am Ali Khalouta from Farhat Abbas University of Algeria. First, thank you for your nice presentation, Professor. My question is how to find zero of Metagrapher equations.
To find zero of Metagrapher function is very difficult. I mean, I think there are some approximately they are found, and there are papers by Gorenflo, Luchko, and I don't exactly remember, but various computational methods have been used, and so it is very difficult subject to find explicitly the zeros of Metagrapher function.
Yes.
So
please, another question.
Yes.
What is the difference between the fractional derivative equation in the capital sense and the fractional derivative equation in the Riemann-UV sense?
No, you can have derivative fraction. You can define Riemann-Liouville derivative even if the function is, say, not differentiable. But for defining Caputo derivative, you first take the derivative and then it's fractional integration. So you need a higher order regularity for the function. So that is where the difference is. So depending upon your model or wherever is your requirement, you will model the situation, maybe in case of using Riemann-Liouville derivative, or say, for example, when you are studying fractals, then
yes.
Riemann-Liouville derivative is more appropriate.
No problem. Yes.
That way, because there are so many other derivatives also. So one has to use for application purpose, depending on the situation, whatever is appropriate, you have to justify that.
Yes. Thank you for your nice presentation, Professor.
Thank you.
Thank you.
Okay.
I also have just a small question. I found it very interesting. I have read your paper that you have last mentioned, the one from chaos with the intersection of solutions. And this is to say that, for instance, if that argument condition does not hold, then the solution to the system of the linear system is not going to be unique.
Yeah.
Right.
Yeah.
If you may have intersections between solutions starting from these different initial points.
Yeah.
Yes.
Okay.
So basically, the interesting is that, I mean, this is the way one can look at it. It allows more general class of solutions. So, for example, this curve, if you take, this curve has a bad point here. Cusp is a bad point when you say ODE. And this curve as such won't be a solution of any ODE, but it is a solution of a fractional differential equation.
Yes.
So fractional differential equation encompasses a larger class or is a more general setup, which takes care of such bad points also in a natural way. I mean, they are part of the family of solutions. So that is where I think lot of work can be done in these directions. And zeros of Metagrapher function is a very important and beautiful area of mathematics where a lot of linking can be done, and concept of fractional flow also should be investigated more deeply. How two things can be composed? We don't have semi-group property, but then what
Yeah,
is that?
indeed.
How the composition is? So maybe more interesting mathematics will come out of that composition. Maybe more some general another function will come out of it, like Metagrapher series. Maybe some other series comes as a composition. That will be wonderful. I mean, that will be a breakthrough.
Thank you very much.
Yeah. Thank you. Thank you. So I think if there are no questions, I will declare that the session is over, and give my and thank all the eminent speakers for their wonderful talks. And I hope the audience enjoyed this symposium, and some students or new researchers have got some motivation and to link special functions to fractional calculus. Thank you.
Thank you.
So
Thank
over to
you,
Dilip
Professor
Kumar.
Varsha. Thank you, Professor Varsha, for nice and insightful your talk on Metagrapher functions. And really, this session was very interesting because we had a good number of talks on this fractional calculus in various aspects of fractional calculus. In fact, the fractional calculus images to various deep insights like Prabhakar Kernel of Metagrapher functions, or it can be right functions of various types, or it can be the fractional order differential equations, or the deep-rooted analysis of this fractional differential equation. So it is nice hearing these sessions, and I think that this participants are also very much benefited from this session on fractional calculus. In fact, we had a paper presentation session also on fractional calculus today, so it was nice. So I thank Professor Virginia Kyriakova for her presentation, also Iva Kaslik for her nice presentation, Francisco Menardi, even his busy schedule, he has taken time to deliver a talk in this area. Sachin Phalekar sir, thank you very much, and Varsha ma'am for organizing this symposium. It was really nice and a beautiful selection of papers also. So thank you, dear participants, for today's session. We are just closing today's session, and tomorrow we will be joining back at 9:30 a.m. for the 9th session. And tomorrow is the last day of our conference. So tomorrow we will be joining at 9:30 with Professor Bruce Byrne. Will be talking on infinite series identities involving a large class of arithmetic functions and Bessel functions. And later we have K.R. Vasuki on Gosper and Lambert series identities, and Gaurav Bhatnagar on an elementary proof and extensions of Ramanujan's convergence. So, and Professor Kalyan Chakravarti will chair that session. So, for today, thank you all participants. We will be coming back.
Switch on their camera, we can take a screenshot actually. So
yes,
can
yes,
you tell
yes.
everyone to switch on their camera? Please switch on your camera.
Yeah, that's a good idea. To switch on the camera, all of you can, if those who can switch on, please switch on their camera so that we can have a click.
Yeah, I think.
Yeah, just a minute. All of you, please switch on your camera, please. Please, those who can switch on, please switch on the camera.
I think people have left.
Yeah.
Now many are just trying to switch on, so we can wait.
Yeah.
some time, people are switching on, I think.
Though it is online, it will be a good memory for us. Yeah. Thank you, Barsa Madam, for organizing nice session.
This
Thank you all.
online,
Thank you all for this nice event.
Yes, yes. Thank you. Credit goes to you as well.
yeah, thank you.
So thank you all for switching on their cameras.
Yeah. Dilip, can the student take the screenshot?
Yeah, I have taken the screenshot.
Yeah,
have
I have also taken. Yeah. Thank you.
Yeah.
Okay, thank you.
So thank you all. Thank you all.